Good morning and welcome to the last day of Solution 2, or I guess good evening or good whatever it is wherever you are. My name's Clint. You may know me as Sauce Control on the Discord or on GitHub. I've also just joined Blue Sky because everybody's gone over there. I didn't tweet much, but I'm going to try to be more active on there and see if we can actually get a developer community going on Blue Sky. So you can find me on there under saucecontrol.us. I have a lot to cover today, so I'm going to go relatively quickly through this stuff, and we'll save time for questions at the end. And I'm just going to jump right into it with the topic of the talk. C# is faster than C++ with many bangs, so you can tell I am super serial. Or maybe you got that it was a joke because everybody knows that C++ is faster. Well, actually, that's not the joke. And I'm going to show that C# is faster. So we'll get to that later. But let's talk about the joke first. Because there's kind of this theme that plays out over and over again, where someone who has, let's say, an affinity for a certain language, who is proficient in that language, and who knows how to write efficient software in that language, will code up a little toy project or a benchmark, and then they'll code up the same thing in some other languages. Maybe languages that they're not so familiar with or don't know the performance characteristics of or whatever. And they'll run them side by side, and surprise, surprise, their favorite language always wins. And they announce loudly to the world, my language is the bestest and the fastest. And hopefully they publish their code when they do this so that other people can check it, because otherwise it's pointless. But the next step that happens is that fans of the other languages come out of the woodwork to say, you got this all wrong. You did X when you should have done Y, and you did Z, and people who know my language never do Z. So I fixed it for you, and now my language is just as fast as yours. And of course, that's how it plays out, because performance isn't fixed, and it's not determined by the language. We actually, I was going to dig up some examples of this because it does happen pretty often, and it's kind of funny. But there was kind of a perfect one that popped up last week on Twitter X. So somebody wrote this benchmark that does a billion nested loop iterations, and they built this little animated visualization to show the speed difference between them, showing that C is the fastest language. And then he says, not all programming languages are created equal, bang. And then somebody's added one of these little context notes on here to say, hey, the Node.js one that you showed as being the slowest is unoptimized. I fixed it, and now it's the second fastest. So this is pretty much the whole trope in one screenshot. Something stood out to me about this, though, was that he said it's C with GCC-01. It's kind of important, actually, when you benchmark C or C++ to say what compiler you used, because the performance characteristics of the different compilers can be wildly different. So it's actually good that he said which compiler he used, but it's really odd that he said GCC-01. And I'll show you why he did that. So this is Godbolt Compiler Explorer, where we can put in some C or C++ code, and then we can compile it in different compilers with different compiler options. And you can see, so first of all, the -01 is the optimization level. So -0 would be no optimization at all. That would be your debug code. 01 is minimal optimization, and it actually goes up to 3. And you can see here, if I take his code, which let me just show you, this is the site where it was originally put. So this is the animation visualizing just how fast C is compared to everybody else with Node.js bringing up the rear, which is why someone had to correct him on that. And then here's the code. And you can see that the code looks the same for all of them, but obviously the compilers and the runtimes and the performance characteristics of these things are very different. So, so if we look at the output from the GCC compiler with O2, just the next level of optimization up, the compiler sees that this loop doesn't actually do anything. It loops a billion times, sure, but all it's doing is incrementing the value or adding a value to an array. So it's created this array, it's adding a value, and then it just disappears and the program exits. There are no observable side effects to this program. And so GCC has said, this program doesn't do anything, let's just return. And you can see here, I wrote the same exact result here by just doing return 0. These compile to the same thing. Main and same exact thing are both just return 0. If I change this to -01, you can actually see why C ran 1 on his benchmark. It actually did some work. Here you can see the loops where it's got these jump statements. JNE means jump when not 0 back up to L2. And so it's actually doing some subtractions and some loops. It's optimized the whole loop into just counting down. It's not doing any of the memory access or any of that stuff. So of course it's fast. Now, not all compilers will throw away work. Clang, for example, a different C compiler, auto-vectorized this loop so that it's actually doing all of the memory accesses and additions and all that stuff, but it optimized it. And then MSVC also threw it all away. I don't know if we can get it to not do that. 01 is also optimized in MSVC. But anyway, so that was why it won, because GCC is basically cheating by throwing away most of the work. And of course, if you can get another compiler to do the same thing, then it'll win too. So that's the joke, is that the whole question, which language is faster, is fundamentally flawed. Languages don't have speed. A language is simply a way to express a program. And in theory, all Turing-complete languages can represent any program. So it's really about how is that program converted into actual instructions that will run on actual hardware, because that's what determines the actual performance. So that's the explanation of the joke, is I'm going to show you that C# is faster, but as soon as I publish the code, which I actually already published it, it's up on my GitHub under Solution2 if you want to poke around already. As soon as somebody sees that in C++ and figures out how it works, they could do the same thing in C++ and it would perform the same way. So I'm spoilering the end of it, but that's the joke. But I am going to show you, I think it's important to understand where this misconception that languages are fast or slow comes from, why there is this predisposition to believe that C++ is faster, and what that actually means and how it gets that reputation and how it keeps that reputation. That's kind of what we're going to do. But we will end by showing that C# is definitely faster, for sure. So let's go back over here to here's my slides. So I think a good example of the fact that these things can change is if you look back in time, it's kind of hard to remember when .NET was actually maybe as slow as people considered it to be, because we've made great strides in the last decade or so. If you go back to 2016, Microsoft decided that they were tired of showing up at the bottom of the Tech and Power benchmarks. And I think it's important to point out that benchmarks are not an absolute measure of performance. A benchmark can only measure this specific thing implemented this specific way at this specific time. And all of those things are subject to change. What that means is if C++ is faster at this one thing, it might not be faster at a different thing. Or it might be faster the way this is implemented currently, but we could implement it differently and that wouldn't be true anymore. Or it could be that it's faster today, but .NET 10 comes out and now it's slower. So any of those things are subject to change. And the ASP.NET team proved that in 2016 when they registered an 85,000% increase in the plain text result for ASP.NET Core on the Tech and Power benchmarks. And the only reason that happened was because they optimized ASP.NET for that benchmark. They got tired of sitting at the bottom of the list and decided they wanted to be at the top, and they made it happen. And they made it happen in C#. The reason being, of course, that you can always do that. You can always find the performance if it's important to you to do so. Now, finding the performance for a benchmark is kind of pointless, and a lot of people accuse them of cheating, because ultimately that benchmark project was not running your standard ASP.NET app, Of course it wasn't. They optimized it. They stripped the runtime of the framework down. They cut out every feature they didn't need. They did some ugly optimizations in C# still, but ugly C# code to get it to be faster, which, you know, for marketing purposes is fine. If you're appearing at the top of the list, at least when people say you're slow, you can say, "Nuh-uh, look, we're sitting at the top of the list." But all of us actually benefited from that, because a lot of the things that they had to do to ASP.NET to make it fast ended up migrating back into the product. And it even kind of motivated some improvements that were made to the language, to the runtime, and to the base class library, such that over time, the ugliness of that benchmark project has decreased as they've replaced their own mangled, hacked up code with just regular calls into the BCL that we would all use every day. So we've all benefited from this effort, but all it took was simply the willpower and motivation, and some skill, obviously, to decide we don't want to be the slowest anymore, we want to be the fastest. Now, in general, C++ is considered a faster language. And when you talk about comparing C++ to C#, these are the kinds of things that people will point out as the main contributors to the difference. So C++ has a minimal runtime. It's got just a tiny amount of startup overhead, and its steady state overhead once your program is running is basically zero. Whereas .NET has a fully managed runtime, and you know, all of your code is running in a VM. We have a larger startup time. The steady state overhead of the VM, the runtime, could be very close to zero, depending on what you're doing. But we also have features within the VM that, if you use them, are expensive and, of course, are going to cost you. Reflection is probably the primary one of those that you'll think of. And that's part of why a lot of the effort going into the performance of .NET recently has been in removing reflection from a lot of places. That's also to support native AOT, native ahead of time compilation, which is exactly what C and C++ do. With native AOT, you end up getting a stripped down minimal version of the runtime, so that reduces your startup cost as well, getting very close to the startup cost of most native compiled things like C++ or Golang. The next thing that people will point at is your explicit memory management in C++. You knew something, that allocates some memory, you delete it, it's gone. In .NET, we have the garbage collector. We have fully managed memory. The garbage collection is lazy, so we accumulate a lot of objects in memory, and then the garbage collector has to go clean them up. If you watched Mike's talk yesterday, he pointed out quite rightfully that if you don't create any garbage, the garbage collector doesn't have any work to do, and it's not going to slow you down. So we don't have fully deterministic and fully manual explicit memory allocation and free in C#, but we do have the ability to avoid allocations if we want to, and that will improve your performance. And that's why over the last many .NET versions, since the split to modern .NET or .NET Core, whichever you want to call it, a lot of the videos, a lot of the performance blog posts, those things focus very heavily on reducing allocations, because less allocations, less GC time, more performance. So I'm basically pointing out that although there are differences, and depending on how you use .NET, those differences can be big, there are also escape hatches. You don't have to use the slower parts of .NET if you don't want to, or if they are harming the performance of your app. You can always take that escape hatch and make it better. This next one is kind of interesting, because C++, first of all, has the standard template library, which, being C++ templates, they're what we would call a zero cost abstraction. Templates in C++ are essentially, when they're compiled, they're kind of copied and pasted by the compiler with the template arguments replaced. So there's really no abstraction or runtime overhead associated with them. So they call them zero cost abstractions. that's one of the things that C++ and Rust programmers especially will pride themselves on, is the fact that they have all these zero cost abstractions, whereas your other higher level languages, we pay for a lot of those abstractions at runtime. But it's also generally accepted and generally true that the libraries that C and C++ programmers use on a daily basis are more optimized than what we have in .NET. And this is getting better over time as well. If you go back, let's say 10 years in .NET, most of what we had open source wise was a bunch of Java libraries where someone had ported it to .NET and renamed it from J whatever to N whatever. Those things generally perform poorly because they were written in Java style, and if you port that to .NET, you're going to have a bad time. We also had a lot of things where people had taken basic old C libraries, like say zlib or libjpeg or something like that, and just ported those directly over to C# as well. And those also perform poorly because if you use the same kind of style of programming, like arrays and things like that, those become managed objects in C#, whereas in C they're zero cost abstractions as well. So this is getting better, but it is still a mixed bag. Of course, we have the base class library, and it's getting better every year too. So this is evening out. Your escape hatch here, which you do still have one, is you can always write your own functionality and make it faster if you have a problem. And then the last thing people will point out is that C and C++ compilers are much more advanced in terms of optimization than our JIT compiler. And there's really two parts of this. One is that AOT compilers, you put in all the work to do the compilation before you ship the program so that it's just running native code from the start. Whereas JIT compilation, that compilation has to happen as the methods are called. They're compiled just in time to be run. We have mitigations for that in .NET as well. We have ready to run, which allows you to pre-JIT compile all the methods in your program, and then the JIT has the option at runtime to improve upon that compilation if it thinks that's beneficial. And then we also have native AOT again, which can fully AOT compile your application. But the JIT compiler, being a JIT compiler, needs to be able to operate in an environment where everything is JITted. So if you imagine you've got a Windows program that's got 2,000 methods in it that need to be compiled before your program starts, how long are you willing to wait for that JIT compilation? Compiling a program with 2,000 methods in C++ might take you, I don't know, 30, 40 seconds. In C# and in .NET, we would expect that program JITting 2,000 methods to take less than 2 seconds. So the amount of time they have to spend optimizing things is pretty vastly different. And so you're going to see that C and C++ compilers do a lot of optimizations that the JIT compiler just doesn't do and isn't going to do because it's never going to have the time budget for that. So our escape hatch here as well is to learn the tricks of the compiler, pay attention to what the compiler is doing with your code, and you can always make it better, or at least let's say help the compiler out to give you better code. I don't have time to go into all the details of all of these things, so I'm going to suggest some videos from .NET Conf. Actually, just the recent one from last week, there was a deep dive on native AOT that covers how that works and what's in that stripped down runtime that you get when you do native AOT compile. There was a good talk on the new features in the .NET 9 JIT, some new optimizations that the JIT can do that it just learned. And last year's .NET Conf, there was a talk on dynamic PGO, which is actually a trick that the JIT compiler has that native compilers don't have. In that native compilers compile your program before it runs, and that's set in stone at that point. Whereas the JIT compiler can watch your program run and see that it's being used in a certain way and optimize for the way it's actually being used rather than deciding all of that stuff in advance. So watch those. Again, I've put all this stuff out in a GitHub repo, which I'll show you a link later. And I've got links to these videos in that repo. Let me check real quick and make sure. I saw I had some pings on Discord. I want to make sure there was just announcements of this. I want to make sure there wasn't a problem. So let's talk about how compilers make your code fast, because I don't have time to go over all the performance differences in detail. That kind of high level summary I just gave is all we're going to have time for. But I want to drill into the compiler side of it, because that's kind of an area of interest of mine. So and I'll be clear here, I'm not a compiler engineer, and compilers are incredibly complex machines. So I'm not going to be able to give you the full picture of this, but I roughly, in my own personal mental model of what compilers do, these are the major categories of things that I think are important. The first one is that the compiler's job is to unwind your abstractions. Now, as programmers in high-level languages, we use a lot of abstractions because they make our lives easier. We have, we build interfaces for things. We build multiple levels of inheritance. We factor out methods to clean up our code. All of this clean architecture stuff where you're adding abstractions potentially just for the sake of having abstractions, where you've got interfaces that just have one implementation. All of those kinds of things cost you, in that those abstractions are code, and if that code actually ran, that's going to take CPU time, and that's going to make your program slower. So if the compiler can see through your abstractions and understand what is and is not necessary, it can start unwinding those. And the more of your abstractions it can get rid of, the less code's going to run, the faster it'll run. So that is a big job that optimizing compilers do. Again, the C++ and Rust programmers will talk about their zero-cost abstractions. We do have some of those in .NET. For example, when you build generics over struct types, those will be compiled individually. I won't say just like a C++ template, but very similarly to a C++ template. So there are some controls that we can exercise over that, but mostly you're leaving it up to the compiler to undo the things that you do to make your life easier. The next thing that compilers do that's kind of important is rearranging your code. So if you have two bits of code that are usually used together, the compiler will actually put them close together in the binary image, or in the compiled image, so that when one of them is loaded into memory cache, the other one goes with it. And then when they're called back and forth, they're close together, they stay in cache, and it's going to run faster. They'll also rearrange the code within your methods. So if, for example, you've got a method where the very first thing you do is say, if this argument is null, then throw an argument null exception. Well, the compiler knows that that's an exceptional case. Exceptions should be exceptional. It should be that your code's going to skip right over that and go ahead and run the rest of the method. So it'll take all the code for setting up your throw and all that, and it'll move it right down past all the real code so that it's out of the way. So it's doing things like that. And PGO is involved in that as well. So both of these first two things are things that dynamic PGO will do that we get in .NET that maybe other languages are not going to have. The last major category that I like to think of is micro optimizations. And that's just the compiler knowing what hardware you're going to run on and knowing the performance characteristics of that hardware and optimizing your code for it. This is the area that I find most interesting. So we're going to talk about this mostly in here. So I'm kind of giving you a high level picture, and then we're kind of drilling further and further down. And I'm just leaving all this other stuff behind, but there is tons of information about it. So we are going to focus on micro optimizations. Make sure we're running on time here. So the title of this talk, I guess we need to get into that. The C# is faster than C++. I need some way to prove that. And I need a realistic scenario, and I need to avoid falling into the trap that I described earlier, where like a C# programmer, and I was a C++ programmer long, long ago, but I'll be quite honest and say modern C++ is gibberish to me. So I would not consider myself a C++ programmer today. And so if I, as a C# programmer, sat down and wrote a benchmark in C++, it'd be very easy for me to make a mistake, or for someone to just claim, you didn't know what you were doing, that's why C++ was slower. So I wanted to find myself a C++ benchmark where someone had actually tried really hard to make this C++ as fast as they could possibly do. And I remembered a couple of years ago, I saw this Stack Overflow question where someone said, how do I make pre-multiplied alpha function faster using SIMD? Now, if you know me from the Discord, you knew SIMD was going to come up in this talk, and here it is. So I saw this a couple of years ago, and I thought this is just the perfect thing, because I've got this C++ program that's been heavily optimized, and all I have to do is beat it in C#. That's got to be easy, right? Well, if you don't know what that means, pre-multiplied alpha, I actually Googled this, and it wouldn't be a talk in 2024 if I didn't have a mention of AI. But I Googled it, and I actually got this nice AI overview that was useful. So it shows, here's what the logic is, and it had an explanation of what it is below, but I couldn't fit it all in the screenshot, so I'll just explain it. So what this is when you build graphics programs, and you've got images or graphics that have varying transparency, and you want to show them on the screen together, you basically need to stack these layers. And the way you do it is each layer has in each pixel, it's got a red, green, blue value and an alpha value that represents the opacity. And then you take, so you're taking a view through all of those layers where the opacity of each image obscures a certain amount of the image behind it. And the way we do that mathematically is you just take all the color channel values, you multiply them by the alpha value, therefore scaling them down according to how much they should contribute to the final image, and then you can just add them together. So the basic idea there is that the composition of the layers is super easy. It's just adding, but the pre-multiplication has to happen before you can do that, and that's a little bit harder. I mean, it's pretty simple code. This is C code, but if you switch out unsigned char here for byte, it could also be C# code. And so what it's doing here is it's reading that alpha value, which is going to be, they're assuming RGBA or BGRA order here. So reading that third byte and then multiplying each of the other 3 bytes by that third byte. These are byte values which are essentially values between 0 and 1 scaled up by 255. So you have values between 0 and 255 representing values between 0 and 1, which means that if you multiply 2 of them together, the total value is now going to be 255 times, it's going to be scaled an extra time. So it'll be 255 times greater than it should be. So then you just divide that by 255, you've got your final pre-multiplied answer, and then you write that back out. So we're reading the alpha channel, but leaving it alone, multiplying all the colors by the alpha, and then dividing the result by 255. So it's a pretty simple algorithm. And this came up actually recently on the Discord, and somebody said kind of the perfect thing here. Pre-multiplying is easy, but making it fast is hard. So that's what this question was about on Stack Overflow, is how do we take this and make it fast? And you can tell this is C++. It looks mostly like the C code, except it's got all these static cast syntax in there, so we know it's C++. Anyway, I'm going to show you that benchmark because I pulled it down and I modified it a little bit just so that I could compile it in multiple compilers. The person who wrote the benchmark built it in Xcode, which uses Clang underneath, and he used a lot of Clang specific directives and even some Clang specific code. So I had to change a couple of things just to get it to run. But one thing I didn't do is I didn't touch any of the math that was in there. So this is all his code, plus the contributions that he got. And I'll go back over here to my this. And he's got, I don't know if you can see it. Oh yeah, you can see it in here. So he wrote a couple of different versions of it using different possible ways of doing it to try and figure out which one was fastest. And you see here he asked for advice on the Discord hash include Discord, which is our I guess C++ sister Discord server. And then he asked on Stack Overflow and got some answers from there. And he put together this actually really good benchmark that compares all of them. And I'll tell you what's good about the benchmark. If you watched my talk last, or for Solution 1, was that 2 years ago? I talked about benchmarks and some of the pitfalls that people fall into measuring things improperly. But this is actually a really well-constructed benchmark that this guy built. He used multiple different methods of performing the same math, getting more and more complicated and ugly as you go. But I'll tell you what he did properly and well that I really enjoy is he used a proper benchmark runner called Google Benchmark. So he's not just doing a wall clock timer and you know, eyeballing the measurements. He's actually using a proper benchmarking tool. He built tests into the thing. So he's got some known answers for correct things. And then he runs these tests with different lengths, testing to make sure you're not overrunning any buffers or mixing your pixels together. So this is really well constructed. And I thought it was just kind of the perfect thing to take this well-written benchmark written by a C++ developer and then make it fast by calling into a C# version of the same code, which hopefully will run faster. Now, if you didn't know that you could do that, that's worth looking at. So I'm going to show you how we do that in .NET. I've got here just a regular C# program, or sorry, it's a C# class library. So, and I've got this class called pre-multiply, and then I've got some methods in it, and then I've got some implementations. And then I've got this class called native exports. And so all I'm doing here is I'm taking a regular C# class library project. Let me show you the project file. The only thing that's unusual about this project at all is that I've got this publish AOT property and then a couple of AOT specific optimization settings. So this publish AOT says that when I publish this, I want to AOT compile it, but until I publish it, it's just a regular C# class library. And I named it appropriately because we're going to be calling it from C++. I'll point out here well, actually, I'm going to save that for later. I'm going to come back to that. So here's how we make it so we can call it from outside of .NET. So we can call it from the C++ benchmark. We declare these methods with unmanaged callers only. That makes these methods that you cannot call from managed code because they're going to be compiled differently. And then we define an entry point on these. This is going to be an export in a native DLL when we publish this with native AOT. And so this is what we would call, from the C++ side, we will load up the DLL or .so that we create by compiling this dynamic library, and then find this entry point and then just call it. So that's all there is to making this callable from native AOT. Or sorry, from C++. And I'll show you actually how this works. Actually, I'm spoiling my benchmark results here, so let me just pull up a new prompt. So let's see, Solution2. So if I go and I run .NET publish on my .NET lib project, and I put in a rid of, this is going to be Linux x64. And to show you how this works, I'm going to put on I'm going to turn off the terminal logger so we can see all the detail as it comes out. And I'm going to set this to normal verbosity. So again, here, the folder that my library is in here is called .NET/lib. -R is for the runtime identifier. Because we are native compiling this, it's actually going to pre-JIT all of the code for specifically Linux x64 and create a native binary. And then here, this last bit here is just so we can see how it works. Oh no, I don't have it. I'm using .NET 9, which isn't in the Ubuntu package manager yet. So I've got that in my home folder. Oops. There we go. Scroll back up past all this view. So what you're seeing here is that the first thing that's happening is that it's just running regular .NET against the CSC DLL. So this is running the Roslyn compiler, and it's telling it just to create a regular old managed DLL. This is exactly how you're going to compile any class library in C#. And so that's going to create a managed DLL, which was called C# go brr.dll. And so that's the output that it put in there in your bin folder. And then the next step that's going to happen is we IL compile this. So this is running the ILC compiler. This is the native AOT compiler, and it's hidden all of its arguments in this response file. But basically, it's passing in the stuff that I put in my project file as far as how to optimize it and all of that. And this is going to output some native object files. So it's running the JIT in advance, knowing which platform we're targeting. It's creating binary code for that platform. And then the last step here is that it's going to call whatever your native C compiler is for this platform, in this case GCC, to link it. I want to be very clear here. There is no C or C++ code here. It is already compiled from the C to native code. We're just using the linker from the C compiler because it knows how to build binaries for that platform, and because we already have some runtime generated binaries that need to be merged with our code. So here's my object file that ILC spit out. It's just a .o file here. And then you can see it's got a couple of other, and it's saying it's going to output it to a .so file. So this is a Linux dynamic library. So that's good. And then you see all these other O files. So it's got this bootstrapper.o and then a workstation gc.a. That's a static library. So all these things that are part of the runtime, but you can very clearly see exactly what it's bringing in from the runtime to add to my DLL or to my dynamic native library that it's going to output. So that's how all of that works. And then it outputs the final binaries to the whatever the RID is /publish. And you can see there it's created this .so file. I don't know if that's big enough. There you go. So it's created C# go brr.so. So that's the tie-in between the native and the managed world. So from this C++ benchmark that I downloaded from the repo that this nice person shared on Stack Overflow, I can now call into my implementations of the same thing that are written in C#. So you can see how it's done here. The benchmark is set up where, and again, this is really well designed. So it's got a setup where it takes a predefined piece of data. In this case, it's a picture of a cat. It's got some transparency. So that's the benchmark. That's the benchmark data. It's loading that up, and then it's just in a loop. And this loop is set up by the benchmark runner. It's going to run a number of times that will be determined by the benchmark runner to get an accurate measurement, sort of like benchmark.net does, just less fancy, let's say. And then here he's actually calling the method that we're testing. In this case, it's called pre-multiply alpha SIMD on a class called v6, passing in that data. So this is the inner loop for the benchmark. That's what it's actually going to be measuring. And then he collects the counters from the benchmark runner so that we can show those. Here's how I modified it. So in this case, I'm going to load. I'm going to call a little a macro that I created called loadlib with the lib path, which you can see. I don't know if that shows up there, but it says right there, the lib path is C# go brr.dll because I'm now looking at a Windows build. And then it's going to find the export in there called pre-multiply scalar and pre-multiply SIMD. Those are the two things that I had named over here, pre-multiply scalar and pre-multiply SIMD. I guess I need to make my fonts bigger over here. There we go. So I'm loading up that library. I'm finding the export. and then I'm just saving that into a function pointer, and then I'm calling that function pointer. So I'm calling into the .NET code exactly the same way he's calling the C++ implementations of it. And then the C++ implementations are all in here. And here's actually where I've set up how it knows where the dynamic libraries are. So I'm looking at a Windows build here, so it's going to use the DLL version, but on Linux it would use the .so version. So here's that code. And I'll go ahead and jump into what those results look like. So I've run these already. And here from MSVC, you can see the V1 plain, which is written right here. This is the one from the original Stack Overflow question with all the static casts back and forth and all that. But it's basically that same code that I showed you that the AI generated for how do you pre-multiply. So that's what that is. And you can see I ran that, and the measurements here, very clearly show that the C++ version of it registered 1,000 iterations per second, and the C# version registered 1.93 thousand iterations per second. So indeed, C++ or C# is faster. But I want you to pay attention to the difference in these numbers. So in this case, C# is twice as fast as C++. Here's GCC. And I want to point out, this is GCC compiled with max optimization 03 and given an architecture of native, which tells it to look at my CPU and optimize it as well as you can for my CPU, which is a AMD Zen 5. And this version of GCC, I'm using GCC 14. It says right here, GCC 14. It recognizes my processor and knows how to optimize for my processor. And yet, this version is even slower than MSVC and way, way slower than C#. Interesting, yes? And then here's the Clang version, which it's gotten a little bit closer to how we did in C#, but it's quite a bit slower still. So the question is, how do we do this? And the answer is, of course, that, well, let me jump back in here. The answer is, of course, that you have to be smarter than the compiler. Now, most people, most of the time, will tell you, don't try to be smarter than the compiler. But in certain dark corners of the Discord, we actually celebrate that sort of thing. And sometimes it's actually necessary, because sometimes the compiler gets hung up on what you're trying to do, and it can't figure out how to make it faster. So this is what we're doing. And I'll show you my code so that you can understand why it's faster. And I want to show you the C++ code so you can see why it's slower. We go back over here. So this is the C++ code, and I've loaded it up in the Compiler Explorer. And I've loaded it up with the latest version of MSVC, and I've told it max optimization. MSVC only goes up to 2, while the others go up to 3. And I've told it you can use any instructions you want up to AVX 512. And this is what MSVC came up with. And if you don't read assembly, I'll just tell you what it does. This is the scalar code. It hasn't done anything fancy with it at all, except for one trick, which is that it's doing a trick of integer division by multiplication. So it's basically multiplying by this magic number and then basically shifting to divide to undo the scaling of that number. And that's how it's implemented it. So it's doing a completely scalar loop. Clang has auto-vectorized this thing like crazy. You can see all these instructions that start with VP. These are all vector instructions and using XMM and YMM registers. So it's using AVX2 to automatically do this in a vectorized SIMD form. And you can see it's generated just a ton of code for this implementation, and it is faster than what MSVC generated, which is interesting. Here again, I've told it I have a Zen 5, so use any instructions that Zen 5 supports, and using your knowledge of Zen 5, optimize it just as much as you can. And this is what it came up with. And then here's GCC, and it has generated just an obscene amount of SIMD code. Here, it's, what is it? 700, well, no, yeah, 700 and something lines of SIMD code, and then a bunch of predefined constants that it used for all the magic math it had to do to generate that SIMD code, or to make that SIMD code work. Just crazy amount of auto vectorization. And the final result of that is that it was really, really slow. So this is one of those things that C++ developers will tell you is an advantage that C++ has that we in C# will likely never have, is they can do auto vectorization and we can't. Well, auto vectorization sometimes does a really nice job. It very, very rarely does as well as a human can. And sometimes it does a really bad job. And there's an example of it right there where it's 6 times slower than the same code written in C#. Well, it's actually not the exact same code, because it really wouldn't be, would it? Wouldn't be fun if we weren't cheating. If I go back to the MSVC code here and look at this magic number math, it's multiplying by this big constant 808080801, and then it is, when it's doing this multiplication, that's ending up, I don't want to get too much into the assembly instructions here, but it's doing a 64-bit multiplication and then shifting off 32 bits of it at the same time. And then it's coming down here and doing another shift of 7 bits. Essentially what it's doing is it's multiplying by the reciprocal of 1 over 255, the reciprocal of 255, 1 over 255, except that you can't represent 1 over 255 as an integer. So it has scaled the whole thing up by this obscenely large number and then divided it back out by a power of 2, which is easy to do with shifts. That's the trick. The only problem is, and the reason that mine ended up faster, is that it's loading up this big constant 3 separate times, 1 for each channel, and then it's doing that multiplication 3 separate times. So it's multiplying by this, or sorry, it's here, multiplying by that big constant 3 separate times. I've optimized this in C# by doing a smaller constant that still happens to work and multiplying it just once. So I'm reading the alpha value just once, doing that multiplication and saving that off, and then doing my my multiplication against the color channels using that pre-multiplied value, and then doing the shift to divide it back out. And that gives me the correct answer. I've got tests here, of course, that prove that you get the correct answer. I've implemented it here in a different way, but using totally safe code and using, this is kind of the canonical implementation of pre-multiply. And if I run my tests here, we can see that in the test explorer, I've got a bunch of different implementations here, which I hope to be able to get over, but we're running short on time already. So I've got all these different versions. You'll notice there's some that are marked as warning here. These are add SIMD. These are ARM64 SIMD implementations, which I'm running here on my AMD machine. So you can't run them on here. So these are skipped tests, but they will pass on ARM. They just get skipped on x86. But here you can see I've got an AVX2 version and a scalar version, and the tests all pass. Now I'm going to have to skip ahead a bit, but this benchmark has a bunch of different implementations. So the first implementation is the one that you see from the Stack Overflow question. The second implementation here is this one, which looks a lot more similar to the one I wrote in my test code, where you're just taking the value as an int32, shifting it down to get the alpha bit, and then masking off that byte, and then doing the same multiply, and then reassembling the uint back this way. So that's almost exactly the same as my test code here. And I'll show you what that does. And I'm actually going to run the benchmark unfiltered now because we don't have too much time anymore. So I'm going to run it on GCC. I'm going to run it on Clang. Oops, without the filters, I said. And I'll run it on MSVC, again, without the filters. And here's what we're going to learn. So looking at the MSVC results, you can see here that the plain version again was the first version, the version that looked a lot like the AI generated example. So MSVC ran that at 1.1 thousand iterations per second. Version 2, which was still just scalar code, but written slightly differently, came out slower. So obviously MSVC has done something different with this code. It came out at 910 per second. Here was my reference C# version that I just showed you. It was running around 1.9 thousand per second. And then there's some SIMD versions down here, which I will come back into in just a second. But here's the same results from GCC. And you can see that although GCC did very, very poorly with that first version of the code, it did a lot better with the second version. It got 5.7 thousand iterations per second. So obviously the Discord people had given this guy the information that if you write the scalar code in this alternate way, it'll auto-vectorize better. And sure enough, it did. GCC did a really good job with it. But again, MSVC did a worse job with it. So that's kind of weird. And still we're at 1.9. Notice the C# results will be the same on all of these because it's actually running the C# code compiled by the JIT, not the other thing. And then finally, Clang. 1.78 it did on the first iteration, but 9,000 per second it did with the alternate version, auto-vectorizing that differently. And I can kind of show you, without going into detail how it works, I can show you why that came out better just by looking at the size of the code. So here MSVC now is using SIMD, whereas before it wasn't. So that's why the performance changed of the MSVC version. This SIMD actually ended up slower than its scalar version, so that was bad, but it did auto-vectorize the second form of it. GCC, which got a lot better, went from having 700 lines of SIMD code down to, actually, here's the end of the SIMD code, like 100 lines of SIMD code. So it just generated a much, much more efficient auto-vectorized version of it. And then Clang generated the most optimized auto-vectorized version of it, which you can see right here. This is actually the core of the loop. Oh, here we go. This is the core of the loop, and it's actually using AVX 512 and AVX2 to do it. So that's why it ends up being the fastest. Now, this is just showing you the results of auto-vectorized code, but going back to the question, clearly he wasn't satisfied with the auto-vectorized and asked for some specific SIMD answers. And so people shared these versions using C++ or using C intrinsics for x86 hardware instructions. And you can see that he got a couple of different answers. There's one of them, and then I thought that actually, I thought there was a full answer here, but anyway, you can see it in the C++ code. So here is an example using all these, these are the actual C intrinsic functions. So these are just all direct method calls that translate to x86 instructions. And he's written several different forms of this one that he got from that Stack Overflow answer. And then there's a weird one in here, which is actually using some weird dialect of Clang, which let me just, oops, to do that. So he's using some weird dialect of Clang to create to create something that looks sort of like a vector. He's calling it a U16X8, which is an alias here for X vector type 16. So this is some sort of weird Clang syntax that does cross-platform generic vectorization. But going back to the results, you can see here that this is that X vector type. This is that weird Clang version of it, even written out explicitly, like I want you to use SIMD and I want you to do it this specific way. That still came out slower than the auto vectorized code, which is kind of weird. Here's the different SIMD results that he got. So the first SIMD form came out at slower than the auto vectorized form. This one, written by Peter Cortis, this guy answers a ton of SIMD questions on Stack Overflow and writes some incredibly great answers. It's no surprise that his version is fast. And in fact, this AVX2 version is the same as his version, just extended from SSE to AVX so that it's operating on wider vectors. So these two were the fastest, the AVX2 being like twice as fast as the AVX 512 code that Clang auto-generated or auto-vectorized. But once again, you will see that C# is significantly faster. Why? Not because the C++ compiler is better, but just because if you care enough to solve the problem better than somebody else did or better than the compiler did, and if you really want to make it fast, you certainly can. And I don't have time to go over how it works. Maybe we'll have to schedule another talk for this or something at some point. But the code is published in my .NET repo. I've got this pre-multiply SIMD, and I kind of drew a picture of how it works and why it's faster. Essentially, I changed the math from the way the compiler would have defined it, which we saw that earlier in the auto-generated version of it, or in the just regular compiled version of the scalar code. I just changed the math slightly to this different formula that is easier to calculate using SIMD instructions, but happens to give you the exact correct answer as proven by my tests. And so using this alternate form of it, I wrote it using nice and clean .NET SIMD instructions. A few of them are platform specific, like this AVX2 shuffle and AVX2 multiply high, but the rest of them are using just regular operators like shift and or, which these are intrinsic operators that happen to compile down to the actual machine instructions, the actual x86 SIMD instructions. So this is my form of it, and you can see it is using AVX2 just like the versions did in the C++ benchmark. Here, the AVX2 version being the fastest, it's just using the C version of the intrinsics, MM256, whatever. And yet, C++ is faster. So 23,000 iterations per second compared to the best Clang did, which was 18.1. GCC, the best it did with AVX2 was 15 versus 23 and some again in C#. And then MSVC, the best it could do was 14.5 versus 23 and some in C#. So that is me proving that C# is faster. Again, the joke is that as soon as somebody steals my improved algorithm that I wrote in C# and moves it to C++, it'll be exactly as fast. But the lesson is there's no magic here. The compilers do what they do. Sometimes it works out. That auto vectorization may end up being really, really fast. Or it may look like it's really fast when you compare it to scalar, but it's so much less fast than it could be if you actually did the work to write it yourself. So as always, benchmarks are a tool. They reveal some, but not all the information. And we can always do better with measurement and a little creativity. So I guess we're out of time now, so I'm going to go ahead and wrap it up. I will flip over to the Discord and see if there are any questions, and then I will try to answer some of those. I actually did a lot more slides to show the algorithm and how it works, and to show how Clang ended up making that SIMD intrinsics code faster than MSVC and GC did, and then how I could improve on that by just changing it a little bit more and optimizing beyond what Clang did. but that's kind of the, well, I ran out of time. So if you're interested in that sort of stuff, maybe we can schedule something for a different time. But let's see if there's any questions in here. Scroll back up. Had some SIMD discussion. Nothing in here. That is a good question. So could I show the resource usage? The C# version, I can't separate out whether the C# version actually does have, whether it has more memory usage because the benchmark is running all of them in sequence. But I can tell you it doesn't have any more memory usage. In fact, let me just let me do this. I was going to load up. Oh, where'd it go? I was going to load up the native DLL and just show you what happened. Oh. I wanted the GUI. Dependencies GUI. So open. There's the C# DLL. So this is a native DLL, and you can see it's got 3 exports on it. The 2 that I defined, pre-multiply scalar and pre-multiply AVX2, and then just this one extra for the runtime called .NET runtime debug header that was linked in. So I would encourage you to watch Mikhail's talk that I linked from the .NET Conf last week about how native AOT works on the inside, because he talks more about how that stripped down runtime works and why the overhead is so much lower for these native AOT compiled things than for what you would typically associate with a .NET program. Let's see, is it worth it to use things like aggressive inlining? Yes. So the reason I did that here is because, first of all, I'm competing with C++, so I know what it's going to do in terms of optimization. But yes, there is a reason that I put aggressive inlining on these. Looking at this pre-multiply. So remember I mentioned that one of the things the compiler does is to undo your abstractions. Well, you can think of just factoring something out as a method as being one of those abstractions that it can be beneficial to undo. Because when you call a function, you've got to package up all the arguments that are passed to that function. So the more arguments it has, the more work you have to do to get ready to call the function. Then you've got to jump to whatever memory address that function lives at, and then you run the code, and then you have to clean up whatever you did with all the registers, restore whatever you need to for those arguments, and then jump back. So there's a lot of overhead, or I shouldn't say a lot, there's some overhead associated with that method call. And so the compiler will normally look and say, if this is a very short method where the execution body of the method is very small, then the overhead of calling it is greater than the overhead of having an extra copy of the code. So it will de-factor that code back into all the places that you called it. The JIT will only do that for code that meets certain size thresholds. And this code, although it is very simple and very fast and should be inlined, the JIT won't do it because it's too big. And so that aggressive inlining hint just says, like here in my SIMD code, well, actually, no, I don't even use that in my SIMD code, but like in my native export here, if you call the pre-multiply SIMD method, I try to call the SIMD implementations if you have hardware that supports one of them, but the scalar implementation gets called as a fallback. So that just gets inlined into these places. And that means that when I do my native exports, the native exports will just directly include the code from all of these, not be making a bunch of internal method calls. Let's see, any websites for cookie? Actually, for cookie cutter optimizations, that BitHacks website is actually linked in my repo that I put up. So let me show you this. I actually had a bunch more slides that I didn't get to show you for how this stuff works, but I did put up a repo here. It's github.com/saucecontrol/solution2. That does have links to some of those tools. As far as canned snippets for SIMD and things like that, I don't know of any, unfortunately. But that BitHacks site is a good one for learning some of these tricks around how to manipulate bytes, because when it comes down to optimizing things with SIMD, it's really a puzzle, and I love doing it. That's why I spent a couple hours actually coming up with a faster way to do pre-multiply, just to prove that I could be faster than C++. But it's kind of a puzzle, because you have these instructions that are available to you, and they're limited. So you have to work with what you've got, and you've got to massage and manipulate the data to get it into a form that you can make it faster. And so knowing these kind of bit hacks is pretty important to it. Were the results the same on Windows and Linux? For C#, yes. So because again, I've compiled these with the JIT, they will compile to the exact same, minus calling convention differences, to the exact same code for x64 on Linux and Windows, the exact same SIMD code, the exact same scalar inner loop. It's just the calling conventions that are different. So yeah, the C# code did measure exactly the same on Windows and Linux, but obviously the native compilers for Windows and Linux are different, and we saw they had wildly different characteristics. I'll also show you quickly, because I didn't do this, I didn't run the full benchmarks on my ARM machine. Actually, I didn't even show you the benchmarks on the ARM machine, did I? So let me just run these real quick, unfiltered on the ARM machine. Oops, let that finish. Because one thing that you'll notice is that, again, with the auto vectorization, it can be really unpredictable. So, and here I can show you that, oh, my Zoom, it doesn't work on here, but so the first version, the plain version, Clang did slightly worse than my scalar version, but it auto-vectorized that second version to be a little bit better than the scalar. Using its explicit vector type, it matched about its auto-vectorization. But the C# SIMD, again, I wrote a ARM version that uses the same kind of math hack that I used for the x86 version that ends up being the fastest on that one. GCC did slightly worse with scalar, a little bit better with its second auto-vectorized version, but still worse than C# scalar, and worse, of course, than the C# explicit SIMD. And then MSVC matched my C# SIMD on the first version of it, but then it tried auto-vectorizing the second version of it. It ended up like half as fast. And once again, the C# SIMD wins by the same, with the same speed, 1.9, whatever. So all that code is in my repo if you want to look at it. Hopefully somebody else can run it other than me. C++ is always a gamble whether you can build it, but let's see. Is the machine code generated identical to C? Not sure if they're asking whether it's identical to C. If the C++ is identical to C, yes, except that the C++ is written in templates. Is the machine code generated by the JIT identical to what you would get from C? Yeah, and I actually meant to show you that as well. So if I look at, so if I pull up one of my implementations, so this is my AVX2 implementation. I've got Disasmo installed, which is an awesome plugin. So if I look at the Disasmo of my pre-multiply AVX2, this is the inner loop of the implementation, and this is what it compiles down to. It's just plain old regular AVX2 SIMD instructions. The reason mine is faster is there are fewer of these instructions than there are in the versions that were written in C++. The trick is, and the reason mine is so much faster, is I was able to eliminate two of the multiplications. So I have two multiplies, one for the even values and one for the odd values, whereas the C++ version has two pairs of multiplies. So here's two multiplies here and two multiplies here. The first one is doing the alpha pre-multiplication. The second one is doing a division by multiplication. And I eliminated one of those so that I'm only doing the alpha multiplication, and then I don't have to divide. I don't have to multiply to do the division. That's the trick. Sounds like you're describing optimization as an art. Yes, it is. That's, like I said, it's like a puzzle, and it's a puzzle that I enjoy solving. So, you know, some people sit down and do Sudoku for an hour. I might sit down and do some SIMD for an hour. Anything else? I do want to point out one thing actually in my, I'm going to point out something in my SIMD implementation. So there's 3 different versions here. There's one implemented in AVX2. That's the one that was just ridiculous fast. There's one implemented in advanced SIMD. You saw it's almost twice as fast as the scaler, but the limitations of the instruction set in ARM64 limit the gain that you can get. So, and that's because you end up having to do 4 multiplies instead of 2, because they don't have the same high-low half multiplications that x86 does. And then down here, I've done a cross-platform vector 128 using nothing but vector 128 instructions, nothing platform specific at all. So this benchmark will actually run, or this method will run on both platforms. But there's a gotcha in this, and I can show you in Disasmo. So I'm on my ARM machine now, so this will be Disasmo ARM code, ARM disassembly, and so here's the ARM SIMD code in the inner loop right here, and there's kind of this mess here up at the top of moving things around, and well, it's just a bunch of moving stuff around, moving and shifting and moving and shifting. The reason it's doing that is because of this vector 128.shuffle. Most of these vectors that I've created up here in the top of the code are recognized as constants, but this particular one isn't. And so if I put that vector.create in line and then rebuild this, it converts all that mess that you saw at the top into a single instruction, TBL, which is what I actually meant that to be. And the same thing happens on x86, where instead of generating a shuffle instruction, it'll generate just a whole big mess, and it ends up running like 4 times as slow. So I was going to show that as part of the demo so you knew to fix it, but if you run the benchmarks later, that's going to happen. And so I can go ahead and run these benchmarks. Let me revert that. I'll save it, and I'll run the benchmark project real quick. Since this is on another machine, it won't interrupt anything. I'll just leave that running and make sure there are no other questions. Something I've always been curious about is if compilers optimize for sequential reads of an array. If you have a byte array and try reading 01, 2, 3, does it translate into a single read of 32 bits at once, or how does that work? Yeah, so it will. In a lot of cases, the compiler does that work. It will auto-vectorize to SIMD if it can, and if you tell it to do max optimization. But there's something else that you should be aware of, which is called write combining and read combining on the processor level. So even if you do read the elements, if you read 4 individual bytes one at a time, the processor will actually combine those reads and writes so that the actual hardware execution is still doing it as 32 bits. So you don't typically have to worry too much about that. And that's why my scalar code ended up being, pretty fast, even though I was doing 1 byte at a time, reading and writing. It ended up being faster than the equivalent, just reading an int and then shifting it out. That ends up being slower well, if you write it in C#. Here's my benchmark.net results from those 3. You can see that the scalar version is 66 milliseconds or microseconds. SIMD was a little bit faster. As you can see, you don't get anywhere near the gains on ARM as you do on x86 with the SIMD implementation. But you can see here the XFlat vector is way, way slow, 400 microseconds. If I do that fix, let's put that back and rerun the benchmark. First 2 should be the same, 67, 66, 67, and then 44, 45, something like that. And then the last one, the cross-platform intrinsics here, even with the fix so that it works, ends up at 100 milliseconds, 104 milliseconds. So the cross-platform vectors are a bit of a gotcha because they only have instructions that are going to be common between the different platforms. You have to do certain things the long way. And in this case, what I had to do was I had to explicitly widen the vectors to be big enough to hold the numbers that I needed. And then I had to do 4 multiplies instead of 2. And then I had to explicitly narrow them. ARM has instructions that simultaneously multiply and widen, and that simultaneously shift and narrow. So I was able to cut a few of those instructions back out. And then again with x86, I'm just doing the multiply, and it's doing an internal shift for me. So I'm skipping a bunch of the steps there. And that's why that one ended up ridiculously fast. 2 minutes left. 2 minutes ago. Oh yeah, I guess we're done. So I'm going to go ahead and cut out. Oh yeah, thanks for posting the link in there. I'm going to cut out. I'll hop on the Discord if you have any more questions, or if anybody does want to see the kind of the SIMD tutorial and the rest of that I had prepared but didn't have time to get to, we can maybe schedule something else. So we'll talk about that too. Thanks everybody, and enjoy the one remaining talk in Solution 2.